Hello, welcome to the lecture for Chapter 5 of MRI The Basics for UCSF Biomedical Imaging 201, Principles of MRI. The topic of this chapter is TR, TE, and tissue contrast. If you don't know what TR and TE are yet, we're going to learn that here. Before I get into that though, just wanted to share this interesting picture, MRI, and this was from a set of dogs they actually trained to lie still in the MRI so they could do fMRI studies of their brain activity. And if you've been in an MRI, heard the noise, this is pretty impressive that they're able to train these dogs to do this. So interesting study. I encourage you to check that out and read on what they did there. Okay, so on to hopefully interesting, but maybe less exciting stuff. So today we're going to talk about, first we're going to reiterate how we acquire signal in MRI. Then we're going to define TR, which affects T1 weighted contrast. And we're going to go into TE, or the echo time, and how that creates T2 and T2 star contrast. So just as a motivator here up front, shown these images before, show them again, is that really relaxation, so T1 and T2 are incredibly valuable sources of MRI contrast. You can clearly see here the images look very different between our proton density, T1 and T2 weighted images. And then at the bottom, we take advantage of T1 weighting also for monitoring the delivery of a contrast agent, and in this case, looking at where the blood-brain barrier has been disrupted in disease. And these are all used clinically because they inform differently on what's going on in the underlying tissue. So how, after today, we're going to start to have some pretty clear ideas on how we're going to create these different proton density T1 and T2 weighted images. And the reason these are valuable is that we have inherent tissue differences between T1 and T2, and again, these often change in disease. So I've taken tables here from a couple of different textbooks. So there'll be some slight variability in the numbers, depending on the references that they're using. But you can see notable differences between different tissue types here. And again, this is the source of like the contrast seen on those images, and you'll see in many different MR images. And the way we control this contrast is typically mostly through three parameters: the RF pulse flip angle, which we covered in chapter 3, the echo time and the repetition time, or TE and TR, that we're going to cover in this chapter. So now, to understand how we're going to get both T1 and T2 weighted contrast, you have to remember, where does our signal in MRI come from? And very important to note here that our signal comes from the transverse component. The signal is coming from MXY, not from MZ. Okay, so we want to be keeping track of what's going on with the transverse, or the XY component of the magnetization, because this is the piece that's rotating around here. If we're at equilibrium in Z, we don't get any signal. We just get signal from the transverse, or XY components of the net magnetization. Okay, so looking at a top-down view now of the processing net magnetization, we can look at just vector, for example, MXY, like this. And what's going to happen over time after tip is, and I'm going to draw this here in the lab frame, so you can just illustrate the what's happening here with precession is that, as we recall, MXY is going to precess or rotate around. And we're going to put our RF coil here. I'm going to measure some signal. And the signal that we're going to measure from this transverse magnetization is going to be proportional to this rotation. And another thing that's important to note here is that I'm showing this for a single net magnetization. But remember, our signal also is summed over the entire sensitive volume of the coil. This piece will become very important when we get into image construction a little bit later, and we will solve that problem at that point. Okay, but this is the case of here, or actually neglecting relaxation. And so we want to actually add relaxation into this picture. So that was an illustration of the behavior of the transverse magnetization, but in the absence of relaxation. So now I'm going to add in what's going to happen when we have T2 relaxation is that the lab frame here, our net magnetization is going to oscillate, but it's going to also, the transverse magnetization, as we talked about in the prior lecture, is going to decay as well with a time constant, T2. So in our RF coil, when we create our signal, it's now going to have some decay associated with it. And this, the time constant for this decay, as we learned in the last lecture, is T2. And sometimes this type of decay curve like this is called a FID, or a free induction decay. This is a term coming from NMR, to be aware of. You may hear it used in MRI as well. So now in this animation here, we're going to add on the T1 relaxation as well. And now we're back in the rotating frame. We don't have this precession of MXY, but we have decay of the transverse component happening relatively quick in this animation, and then the growth towards equilibrium, towards M naught with the relaxation time constant T1. And as we showed in the last chapter, it's going to follow these two time curves. Okay, so next we want to examine the behavior of the net magnetization during a simple pulse sequence where we have RF excitation. And so we represent that by, I'm going to use the little arrow here to represent an RF pulse. And how about let's do a flip angle of 90 degrees in this pulse. And then I want to illustrate the net magnetization during this sequence. So let's look at this at certain times. Time 1, right before the RF. Time 2, right after the RF. And then let's pick 2 additional times later on. So over here, going to show the net magnetization. Now we're going to start before the RF pulse with the net magnetization aligned along the z-axis. And if this is at equilibrium, this would be at a value of M naught. MXY be at 0 here. And so if we illustrate that over here, this is our net magnetization pointing along the z-axis. Now after this RF pulse, it's a 90-degree pulse. So now we're going to rotate it by 90 degrees into the transverse plane. And what that's going to look at over here in with our corresponding pulse sequence diagram is that now at this point we have no Z-magnetization. Sometimes we call this saturation. We have no Z-magnetization. We've converted all our magnetization to be transverse magnetization. And then at this point we get the behavior that we saw just on the last slide, where there will begin to be both T2 decay and what's often called T1 recovery. So we have T2 causing the net magnetization here to move inward in XY, and T1 causing the net magnetization to go back to M naught along the z-axis. And as illustrated in the last slide, maybe that's not quite. Eventually, we'll begin to continue to have our T1 recovery and so T2 decay of our net magnetization. And if we're to plot that over here, it's going to look something like this, where our MXY will, well, maybe let's try to draw it accurately with the plot over here. So now we have a curve that's going to be in the shape of exponential decay, and then the a recovery curve is going to be in the shape of 1 minus an exponential decay, the T1 time here. And we'll add in this data acquisition piece in a little bit here. But first, before we focus on the data acquisition, and let's look at what we can do actually with repeated RF pulses and T1 recovery to create T1 contrast. Okay, so we can extend this picture to actually create T1 contrast by in fact applying multiple RF pulses. So then we begin again here with our 90-degree RF pulse, our magnetization at equilibrium. I have a 90-degree tip here, and then we're going to have some amount of T1 recovery, and then we'd also have the corresponding decay of the transverse component. And so what this is going to look like in terms of the net magnetization here, you can imagine it's pointing upright, z-axis is tipped into the transverse plane, and then by the time, after we wait some time and we have the T2 decay is mostly complete, but let's say we don't have complete recovery of the Z component, right? So we can choose the time of this 90-degree pulse to say such that let's be at a time when we actually have not reached equilibrium. And if we apply another 90-degree pulse, at this time, we're going to take our net magnetization here, tip it back down into the transverse plane, like so. But as you can imagine, in the first case here at the beginning, the length of this vector was m naught, but now since we didn't allow for complete T1 recovery, the length of the net magnetization is in fact less than m naught. So what is this effect is this going to have on our signal? Is that when we play the second 90-degree pulse here, the transverse magnetization that we will get will actually be smaller. And how much smaller? Well, it'll depend on how much T1 recovery happened in this time interval right here. And then we can repeat the same process with these repeated RF pulses. And these are going to have the effect of creating, this is exactly how we create T1 weighting. So let's expand this a little bit further and define the concept of repetition time. So here we have, and say this could be any flip angle, but do it as a 90-degree pulse here. So the repetition time, or TR, is the time between these successive RF pulses, these successive excitation pulses, where after each one of these, we'll assume there'll be some amount of turn on our data acquisition, acquire some signal. And remember that our, say that this amplitude up here is M0. What's going to happen in this case is maybe initially the net Z magnetization will be at M0, but then because we choose the TR to be, in this case, less than T1, or it can even be similar to T1, we're going to end up in this case where the Z magnetization does not return to its full amplitude. And we have some partial recovery of the Z component. What this is going to do in the transverse component is, if this is, when our transverse component is M naught, after the first pulse, it's going to be a full M naught. Going to decay. But at the second RF pulse, you can see the amount that it's going to tip into the transverse plane here is less than M naught. So it's going to tip some smaller amount, and you can see in this drawing that the amount of signal that is going to be received is in fact going to be smaller when we are under this condition that the TR is similar or less than the T1 value. So let's derive more specifically what the signal is going to be related to. And in this slide here, we're going to use the same pulse sequence, the repeated 90-degree pulses. Okay. And let's add our M naught line up here. Okay. We're going to start off, MZ is equal to M naught, do a 90-degree pulse. We're going to get some amount of T1 recovery. And what's going to happen with these 90-degree pulses is let's call this the signal we get at time 1 here, going to be proportional to whatever the MZ was before the RF pulse, so M0. But in this case, let's figure what's in our second TR here. What is our signal going to be proportional to? So we apply this 90-degree tip, and basically we want to know what is this value up here. So we're going to use our equation for T1 relaxation, which is going to be mz at time 0 e to the minus t over t1 plus m naught 1 minus e to the minus t over t1. And recall this applies, you can use this between RF pulses. So what we have here is we want to figure out what is, we have mz at 0. In this case, let's say this would be t is 0. It's right here. And this time right before this is tr. Now we use our definition of tr. mz initially is 0. This is what we've created after the 90-degree pulse. So mz at this time tr is going to be mz0. This first term is gone. It's simply going to be m naught 1 minus e to the minus tr over t1. Okay. Yes, we've got there. We've got t1 waiting in here because we have some term in here that depends on t1. In fact, then the signal that comes out in this second tr is just going to be proportional to this mz of tr, which is m naught 1 minus e to the minus tr over t1. Okay, so we have a t1 weighted signal that we've created here. Now another thing I want to point out is if we repeat this again, we have the same time interval here, tr, that in fact the evolution of our net magnetization now between this and all subsequent TRs is exactly the same. We have the same time interval TR. In each TR we have the same initial condition. We always start with, at this time we always have 0 Z magnetization. So the signal in this third TR is going to be proportional to the same thing, m1 minus e to the minus tr over t1, and the signal in the fourth TR, and so on. It's going to be equal to the same thing. One thing we say that we have when this happens is we would say from this time point of the second TR here onward. So from this point on, we say we're in the steady state. That means things are consistent TR to TR. Okay, so this is, and we're going to go over this again, but do something where we're going to start to change the flip angle when we get up to in a couple chapters, up to chapter 7. That's going to be variation on the same theme here of creating T1 contrast by using repeated RF pulses. So here are some examples of brain images acquired where actually all I've done is the same repeated 90-degree flip angle pulse sequence. but just varied the TR. So what these curves are over here are simply curves that are m naught 1 minus e to the TR over T1, where the T1 is now chosen differently for these different tissues. And also, I think they're also accounting for different proton densities, or m naught, for the different tissues. And what basically is happening here is usually the strongest T1 contrast is typically at the shorter TR, so this TR of 250 milliseconds has a more characteristic T1 weighting or T1 contrast for the brain. Okay, so that covers TR, and then the other major piece we need to cover here for generating contrast is the echo time, or TE. Also sometimes called the time to echo. And I've shown a couple other things here before, data acquisition. Just reiterating that is the DAQs, abbreviation that I will use. And time to echo, or TE, is defined as the time from the center of the RF excitation pulse. So in this case, instead of drawing it as just a single point, so we can illustrate this, we'll draw this, what they call hard RF pulse. And then at some later time here, turn on our data acquisition, and this is going to be more of a zoomed view than the previous one. And echo time, or TE, is defined as being time from the center of our RF pulse to the center of our data acquisition. And what the echo time gives us is now not T1 contrast, but gives us T2 weighting, or T2 contrast. So as an example here, let's continue to our example that, say we have a 90-degree RF pulse. So we start M naught Z magnetization, no transverse magnetization. During the course of this RF pulse, Z magnetization will go to 0. And XY magnetization will go up to a value of M naught immediately after the RF pulse. And then after this point, the thing that we're capturing with the echo time, the fact that we have this decay of the transverse magnetization proportional to T2 or T2 star. We'll get more into the differences of when it's T2 and when it's T2 star when you get into spin echoes in chapter 8. So in fact, this case, purely consider this to be in fact T2 star decay. There will be T1 recovery over this time, but when we're looking at what the signal we would get, we'd say we also take the signal to be at the same echo time here. So the signal in this case is proportional to this and we can say, do a little abbreviation here, T2, or add a little parentheses around the star to indicate it could be T2 or T2 star. So, but the point here is this is how we create our T2 or T2 star contrast, is we insert some delay between the RF pulse and the data acquisition. And so again, here we have some plots and images taken at various echo times, where these plots over here are going to be with a spin echo. So it's simply T2 curves that are being plotted here. And the different shapes are because these different tissues have different T2 relaxation times. And there's actually, it's also accounting for, interestingly, T1 weighting in this sequence with this TR. So what you can see here is that you go from what is to this very different contrast as you go from this early 25 millisecond echo time to this later 100 millisecond echo time, and at this later 100 millisecond echo time, this begins to be our characteristic T2 contrast. And here is an example of different echo times in a gradient echo sequence, which is T2 star weighted, and it looks very similar. You'll see to the T2 weighting. And there's some subtle differences that we'll get later into later. But again, the signal weighting on these images will be T2 star. Now we can combine TE plus TR to get both the T1 weighting and the T2 weighting or contrast of a given sequence. So let's look at this again for our repeated 90-degree pulse sequence here. And this is going to be our TR between these pulses. And then I'm just going to, normally what we do when we're doing imaging is we actually start once acquiring data once we're in this steady state. If you want to check back on that concept again from a couple slides ago. So we're not going to do any data acquisition with this first RF pulse. We're going to do data acquisition from the second RF pulse onward once we're in the steady state. Excuse me. And this time we're going to add a little bit of a delay between our RF pulse, our data acquisition. This will be our echo time. And this is both the TR and the TE are kept the same during the scan. Okay, and let's add in our drawing of our net magnetization, and we can actually going to want to come out of this with a solution for what the signal weighting is both with TE and TR. Okay, so we call it with start at equilibrium. MZ is M naught to our 90-degree pulse. Is some small amount of T1 recovery. Now what we derived before was the amplitude of this of MZ here was going to be M naught minus e to the minus TR over T1. And we're hitting this with another 90-degree pulse. And let's add in now the transverse component. So this is our signal component. Starting at 0. The first TR, it's going to go reach sort of a, it's going to reach the maximum value, M naught, but the second TR, our Z magnetization, instead of starting at the full amplitude, as it did the first TR, is going to start at some smaller amplitude. So when we tip it over the first time, it was very large. When we tipped it over the second time, it's smaller. So the transverse component that we're left with here is going to be also M naught e to the 1 minus e to the minus TR over T1. And then the signal is going to decay. And in this interval, we'll have our same amount of T1 recovery here. And now let's add in, okay, at our echo time here. This is our echo time, just drawing that again here, that the signal here at this echo time will be proportional to this initial height. And then keep in mind the shape here is now our T2 decay. So we're going to combine the expressions that were on the previous slides for TE and TR. Contrast, it's going to be first whatever the initial weighting was of the transverse magnetization due to the partial saturation of the V component times the effect of some echo time delay between the RF pulse and the data acquisition. So this is now a signal equation combining both TE and TR that applies for this type of pulse sequence. We're doing these repeated 90-degree RF pulses. And we're in the steady state out here, so this behavior is simply identical between subsequent TRs. Now you can see there's the note on the side here that we typically assume that the transverse magnetization has either decayed to zero by the next RF excitation, or that we use this concept called spoiling that will be covered in chapter 21. So there you have an equation for TE and TR, how they're going to determine T1 and T2 weighting in this type of repeated 90-degree RF pulse. And if you look back at the previous example for the brain images with different TEs, actually the TR in that case was 1.5 seconds, which for something like fluids like CSF, that's actually going to create some amount of T1 weighting as well. So those curves both had T1 and T2 weighting in them. Okay, so we've reached the end of this chapter 5 lecture recording. So make sure when you're reviewing this that you've got these key concepts of, first of all, what is the source of the MR signal in terms of the net magnetization, and know the definitions of TR and TE and how they can be varied, how they can create T1 and T2/T2 star weighting. Thank you very much for joining.